201 million years ago, North America entered the Jurassic after a major biological reset. The continent was still breaking apart, and rifting created basins where rivers, lakes, and life could accumulate. Volcanic ash could disturb a lake in minutes, while quiet water preserved what sank below. Ferns, horsetails, and seed plants rebuilt the terrestrial food base after extinction. A lake was not one environment. Light, oxygen, and temperature changed with depth. Small theropods occupied flexible feeding niches along the edges of recovering waterways. Every flood carried the mountains into the basin grain by grain. Early sauropodomorphs were still modest in size, but their body plan pointed toward later expansion. Lake margins concentrated plants, insects, amphibians, and small vertebrates within a narrow. Small theropods could exploit the dense, obstructed spaces beneath taller plants. One rift basin could contain several climates and habitats within a single drainage system. Decay returned nutrients to the thin soils from which the next generation of plants grew. Armored herbivores filled the low browsing layer beneath taller early Jurassic vegetation. Expanding water opened temporary aquatic habitat, shrinking water exposed new feeding ground. Water was a resource, a route, and a boundary between different early Jurassic niches. Tracks preserve a moment of movement, not a complete biography. The next reconstruction is younger and farther southwest, where seasonal rivers crossed the Kayenta floodplain. In Kayenta country, rainfall arrived seasonally, creating a patchwork of wet channels and dry ground. Rivers now lead us into the first great terrestrial ecosystem of Jurassic North America. Kayenta rivers built their floodplains through repeated pulses of water and sediment. Dilophosaurus was one of the large theropods known from early Jurassic southwestern North America. Wetlands added slow water, saturated soil, amphibians, insects, and a second layer. Saurosaurus shows an early sauropodomorph body plan before the later explosion of sauropod size. A river could create and erase habitats within the same season. Small predators could exploit the brief abundance around receding water. Amphibians occupied the shallow, saturated places that larger terrestrial animals crossed only briefly. Flood disturbance created new ground where pioneer plants could return first. Its long legs and balancing tail suited movement across uneven seasonal river margins. Waterlines and mud cracks record the repeated rhythm of wet seasons and dry intervals. Even a small armored body could exploit food and shelter close to the ground. Monsoon storms could connect distant channels into one temporary flood system. Small predators occupied the narrow boundary between wetland water and terrestrial leaf litter. Trace fossils reveal posture and passage, even when bones were never preserved. River margins offered both water and a concentrated band of edible vegetation. Wetlands stored plant matter and transferred energy into aquatic and terrestrial food webs. Disturbance repeatedly opened space for pioneer vegetation to return. Small bodies could use vegetation as shelter as well as food. North America was a river world, but its rivers ended against a much drier interior. This is a separate early Jurassic world, where wind-built dunes dominated the continental interior. Even the desert held narrow green corridors where water briefly overcame the sand. Herbivores could survive arid conditions by following brief, productive water corridors. Dune movement was slow, but over time it buried channels and redirected every desert route. Small herbivores occupied the sheltered margins that large desert animals could easily overlook. A single storm could create a short-lived island of productivity inside the dune sea. The dunes became stone, preserving the direction and strength of ancient winds. When water vanished, the green corridor contracted before the dunes reclaimed it. Later Jurassic North America became more tectonically varied, with volcanic uplands replacing some earlier dune. In the Middle Jurassic, volcanic relief and changing rainfall created new forested basins across the west. This Middle Jurassic basin is millions of years younger than Kayenta and shaped by different volcanic relief. Volcanic ash could destroy a surface, then enrich the soil that replaced it. Early sauropodomorphs remained part of North America's changing herbivore communities. Lakes preserved quiet margins where sediment, vegetation, and freshwater life accumulated together. Forest layers divided sunlight, moisture, and food long before flowers or grass existed. Forest predators worked within cluttered spaces where distance and visibility were limited. Volcanic landscapes repeatedly redirected water and buried the habitats growing below. Herbivores used different plant layers, reducing direct competition within the same forest. Lake sediments preserved climate pulses more quietly than the storms that created them. This is a cautious regional reconstruction, not a claim that Kayenta animals remained unchanged here. Recovery was uneven, some slopes stayed barren while wet gullies quickly turned green. Before flowers, wind carried the reproductive future of the forest. Long-necked herbivores were expanding their reach before the great Morrison sauropods appeared. Erosion revealed the volcanic history written beneath each new soil surface. Fallen wood created elevated paths, shelter, and concentrated invertebrate habitat. Storms mixed the lake, redistributed oxygen, and gathered organic material along sheltered margins. Herbivores had to negotiate not only plants, but the unstable ground beneath them. Forest recovery began with pioneers, then gradually rebuilt layers of shade and shelter. Shorelines gathered the material that connected forests above the water with life beneath it. Forest predators used openings, shadows, and water margins rather than one uniform hunting ground. Mountain storms joined separate valleys through water, while ridges kept their ecosystems apart. Jurassic forests were diverse without flowers, built from many forms of seed plants and spore-bearing vegetation. Mammalia forms were small, but hidden forest spaces offered them reliable ecological opportunities. Evaporation changed lake chemistry and concentrated life along the remaining water. Water and vegetation together made lake margins valuable to early herbivores. Western uplift was beginning to supply the sedimentary landscapes of the Late Jurassic. Mountains, rivers, and sediment now point toward the Late Jurassic Basin of Giants. The Middle Jurassic forest was a vertical ecosystem, from fern litter to conifer crowns. Small theropods added another layer of movement beneath the larger forest animals. Roots stabilized the ground, while decay returned nutrients to the forest floor. Lakes interrupted the forest and created open shorelines for animals that avoided dense cover. Mammalia forms remained small, but sheltered roots and fallen trunks created dependable microhabitat. Wind disturbance opened light gaps that changed which plants could grow below. Disturbance did not remove opportunity, it rearranged it. Wind and waves mixed the upper water, carrying oxygen into the shallow margins. Beneath the canopy, moisture could remain long after the surrounding air began to dry. Ornitholestes were small enough to use the forest's fallen architecture as a root. Sheltered lake corners gathered leaves, insects, fish, and the nutrients released by decay. Hidden lake margins gave small mammalia forms access to water without exposing them in open ground. In volcanic country, drought could end abruptly when a storm reconnected the basin's water. A fallen tree could become a new clearing, a bridge, a shelter, and a nutrient source. These mountain fronts would feed the enormous Late Jurassic Basin still to come. The next chapter enters the Late Jurassic Morrison Basin, where mountain sediment and plant abundance supported giants. By the Late Jurassic, western mountains were feeding immense sedimentary basins. Each fan spread mountain rock outward, building the floor of the future Morrison Basin. This floodplain was not a single forest, but a shifting mosaic of channels, levees, ponds, and wetlands concentrated oxygen, nutrients, amphibians, fish, and decaying vegetation. Camarasaurus combined a deep body with a broad skull suited to powerful plant processing. The river created both destructive currents and quiet places where fine sediment could settle. Apatosaurus represents the Morrison experiment in immense mass and powerful neck musculature. Wet soils preserved roots and plant debris while supporting the floodplain's living productivity. Diplodocus fed close to the ground, occupying a different plant layer from taller browsers. The Morrison Basin could be wet in one interval and seasonally dry in another. Allosaurus was one of the largest known theropods in the Morrison Predator Guild. Morrison rivers began in mountains and carried highland weather into lowland ecosystems. Wetlands offered softer vegetation and reliable water within the broader floodplain. Every layer of mud recorded a short episode in the life of the basin. High browsers reached vegetation above the feeding zones of lower sauropods. Below the giants, algae and aquatic plants converted light into oxygen and food. The Morrison climate was seasonal, and some storms passed without breaking the drought. Low browsing allowed Diplodocus to use vegetation around shrinking water without climbing uplands. Mountain erosion created the broad lowland stage on which Morrison ecosystems diversified. The Morrison Basin was large enough for many giant herbivores to occupy different feeding landscapes. Diplodocus harvested low vegetation, leaving taller plant layers to other sauropods. A wetland was a mosaic of foods, textures, depths, and temperatures rather than one uniform. Camarasaurus fed above the low fern layer but below the highest conifer crowns. New levees created raised ground where conifers could survive above seasonal floods. Brachiosaurus occupied the highest browsing zone visible in the Morrison forests. The wetland changed with the day, revealing new feeding surfaces as water and fog withdrew. Immense bodies required stable ground, reliable plants, and enough space to move between watercourses. One footprint could become a temporary pool, shelter, and record of several animals passing together. Barosaurus shows how far neck length could be pushed within the diplodocid body plan. During drought, the giant landscape narrowed into a few usable water corridors. Robust sauropods could process tougher vegetation around drier parts of the basin. Water refuges supported life that could not survive on the dry levees around them. Supersaurus shows how geographic scale and plant abundance made extreme body length possible. Floods renewed the low vegetation that supported the basin's largest herbivores. A storm could be visible across the mountains and still miss the animals below. The diplodocid body plan combined low feeding with a long, highly balanced tail. Seasonal wetlands were productive, but never permanent. In the Morrison world, even the giants became small against the geography that sustained them. Different habitats supported different predators, not one simple Jurassic hunting style. River crossings placed predators in contact with many habitats at once. Food webs also depended on plants, insects, decay, and water, not only on dramatic. Ceratosaurus occupied a different body plan and may have used wetter margins than some larger theropods. Storms altered the edges where predators, herbivores, fish, and amphibians met. Torvosaurus added another large-bodied predator to the Morrison ecological network. Seasonal stress divided the basin into habitats with different risks and opportunities. Predators followed the same environmental constraints as the animals they depended on. A wet surface turned movement into evidence, preserving the shared roots of many animals. Morrison North America was a network of habitats, and the final chapters widen from predators to air, water. Ceratosaurus occupied a different combination of body form, water access, and habitat from other Morrison. Even the largest predators ultimately depended on small places where water survived. Torvosaurus added a powerful predator form to the open ground guild. Water could preserve a trackway, modify it, or remove it entirely. Fossils show anatomy clearly, they reveal much less about the precise choices an animal made each day. Vegetation itself mapped the hidden water network across the dry basin. Small organisms transferred energy upward through every Morrison food web. Stegosaurs occupied the low vegetation layer, protected by distinctive plates and tail spikes. North America also faced a western ocean, where land, air, and water formed another Jurassic frontier. The western margin was not Morrison floodplain, it was a rocky boundary facing the immense Panthalasan Ocean. Sheltered lagoons created calmer water and softer sediment than the exposed ocean coast. Turtles occupied quiet shallows where mud, vegetation, and protected water came together. Shallow shelves supported a marine community separate from both open ocean and inland freshwater. Hybridant sharks moved between reef margins and deeper coastal water. Restricted lagoons could become saltier and warmer than the open shelf beyond them. Crocodile-line reptiles occupied the boundary between freshwater channels and protected coastal shallows. Volcanic coasts supplied hard surfaces, tide pools, and fresh sediment to the western margin. Marine foundations were built by countless organisms too small to dominate the image. Turtles added slow-moving, shell-protected life to the lagoon margin. Coastal storms moved sediment between the land, the lagoon, and the open Panthalasan Sea. Sharks connected reef edges with deeper water in the coastal food web. Tides repeatedly redrew the boundary between land and protected water. Beyond the coast stretched Panthalassa, the immense ocean bordering western North America. Ocean life changed with light, depth, oxygen, and the material sinking from the surface. The western coast linked the continent to a world beyond the rivers and mountains. Jurassic North America was never one ecosystem, but a continent of changing regional experiments. Gigantism emerged within landscapes that supplied space, water, and enormous quantities of plant matter. The age of giants rested on processes too small to see from a sauropod's height. Giant herbivores changed paths, vegetation, and soil simply by moving through them. Uplift created mountains, mountains created rivers, rivers built the plains where giants lived. No single predator explains the Morrison ecosystem, several body plans shared its habitats. Soil color and sediment texture preserve changes in water, oxygen, and landscape energy. Armored herbivores added a lower-bodied solution to the same vegetation-rich landscape. The Western Ocean was part of North America's Jurassic story, not merely its distant horizon. Ocean food webs began with suspended production descending from the lighted surface. Rivers connected every Morrison habitat, from mountain sediment to lowland forest and wetland. Forest height created feeding opportunities that did not exist in the low vegetation below. Giant ecosystems depended on roots, algae, insects, microbes, and water. The Morrison predator guild was shaped by forests, rivers, drought, and the distribution of giant herbivores. Tectonics set the slopes, weather carved them, rivers delivered their consequences to the lowlands. Earlier North America held deserts and temporary corridors, later North America held mountain-fed floodplains. The Jurassic began with rifting, and its landscapes remained controlled by the consequences of moving crust. Jurassic North America was not one lost valley, but millions of years of changing worlds. In Jurassic North America, moving landscapes made the Age of Giants possible.